Welcome to Spaceverse, your portal to cosmic adventures. Experiments show that biomolecules trapped in pure ice could withstand the harsh radiation of Mars for tens of millions of years. If life ever existed on Mars, traces of it might still be frozen beneath the planet's icy surface. A new study from NASA and Penn State University suggests fragments of biomolecules from ancient microbes could survive in Martian ice for tens of millions of years, long enough for future missions to potentially find them, according to a statement from the university. In laboratory experiments simulating Mars conditions, researchers froze samples of E. coli bacteria in two different environments: pure water ice and a mixture of water and ingredients found in Martian soil, including silicate-based rocks and clay. The samples were cooled to -60 degrees Fahrenheit or -51.1 degrees Celsius, the average temperature of icy regions on Mars, and then exposed to radiation levels equivalent to what they would experience over 20 million years on the Martian surface. The results were then extended through modeling to represent an incredible 50 million years of exposure, according to the statement. 50 million years is far greater than the expected age for some current surface ice deposits on Mars, which are often less than 2 million years old, meaning any organic life present within the ice would be preserved, said Christopher House, co-author of the study and professor of geosciences. That means if there are bacteria near the surface of Mars, future missions can find it. Now, let's pause for a second. Imagine that something that lived on Mars millions of years ago, frozen in time, waiting for us to find it. This isn't just a sci-fi fantasy anymore. It's a real, testable scientific possibility. The researchers discovered something remarkable. Amino acids, the building blocks of proteins, and therefore life, survived far better in pure ice than in ice mixed with sediment. In the pure ice samples, more than 10% of the original amino acids remained intact after the simulated 50 million year exposure. But in the ice mixed with Martian soil, the amino acids degraded 10 times faster and didn't survive. That's a stunning difference, and it tells us something profound about how Mars preserves its secrets. When the team ran additional tests under even colder conditions, similar to those found on Europa, one of Jupiter's icy moons, and Enceladus, an icy moon of Saturn, they discovered that the colder the ice, the slower the decay. The freezing environment essentially acts like nature's deep freezer, locking away molecular clues for eons. Why does this happen? The researchers have a fascinating explanation. In pure ice, radiation byproducts, known as free radicals, get trapped and immobilized. These free radicals are the unstable fragments that usually tear biological molecules apart. But when they're frozen solid and can't move, the destruction slows dramatically. In contrast, when Martian soil is mixed into the ice, the minerals in the soil seem to create thin films of liquid. These films allow those destructive particles to move freely, increasing the rate of chemical damage. So, in other words, the dirtier the ice, the more dangerous it becomes to the delicate organic molecules trapped within it. That's why Alexander Pavlov, the lead author of the study and a space scientist at NASA's Goddard Space Flight Center, concluded, "These results suggest that pure ice or ice-dominated regions are an ideal place to look for recent biological material on Mars, and that insight could change how we search for life beyond Earth." For decades, Mars has been a focal point of humanity's curiosity, the planet that might have once looked like Earth, with rivers, lakes, and maybe even oceans. Today, it's a cold desert world, battered by radiation and stripped of its atmosphere. Yet beneath a desolate surface, frozen in the planet's polar caps or buried just a few feet underground, there could still be whispers of its ancient past, perhaps the remains of once living things. This study gives future missions a new strategy. Look to the ice. Not just any ice, but pure ice. The implications go beyond Mars. The same preservation mechanisms could apply to other icy worlds like Europa or Enceladus, both of which are high on NASA's list of places that could harbor life. If biomolecules can survive tens of millions of years trapped in ice on Mars, where radiation is intense and conditions are harsh, they might last even longer on these distant moons, where the cold is even more extreme and the radiation less severe. Let's think about what this means for exploration. NASA's upcoming Mars Ice Mapper mission, along with other planned missions like the ExoMars rover and potential sample return programs, might use this new information to target specific regions where pure ice exists. These areas could hold biological time capsules, microscopic traces of ancient life preserved just beneath the surface. And the best part, many of these icy deposits are thought to be less than 2 million years old. That's relatively young in geological terms, meaning any organic molecules preserved there could come from a more recent period when Mars might still have been habitable. Future rovers or landers equipped with specialized drills could dig into these deposits, extracting ice samples for detailed analysis. Scientists could then search for amino acids, lipids, or other biomolecular fragments, the same building blocks that make up life on Earth. If they find them, it wouldn't just confirm that Mars once hosted life. It would also tell us something about how life, once it begins, can endure, even in the most hostile environments imaginable. Let's rewind to the beginning of the story for a moment. The idea that biomolecules could survive for tens of millions of years on Mars might sound surprising, but it's based on a deep understanding of radiation chemistry. Mars lacks the thick atmosphere and magnetic field that protect Earth from cosmic rays and solar radiation. That means anything on the surface gets bombarded constantly by high-energy particles. Over millions of years, that radiation should break down organic molecules completely, or so scientists thought. But this study shows that when those molecules are locked away in pure ice, the destruction slows dramatically. The ice acts as a natural shield, dispersing radiation energy and trapping the harmful byproducts. It's like the difference between leaving food out in the sun versus storing it in a freezer. One decays rapidly, while the other can last almost indefinitely. That discovery reshapes how we think about Mars as a time capsule. It means that even if microbes died off eons ago, their molecular fingerprints could still be there, waiting beneath the surface. This is especially exciting because Mars has regions that are permanently frozen, particularly near the poles, but also beneath the mid-latitude surface. If we can target those pure ice regions, we might not just find geological evidence of past water, we might uncover actual biological remnants. Think about it. A frozen archive of Martian history preserved for 50 million years or more. And what if we take this even further? If biomolecules can survive that long in Martian ice, then similar preservation could happen on comets, asteroids, or icy moons, meaning that the ingredients of life might be widespread throughout the solar system. It supports a growing scientific idea that life's chemistry isn't unique to Earth, but could emerge, or at least persist, wherever water and the right conditions exist. The findings from this NASA and Penn State study aren't just a technical milestone. They're a roadmap guiding future explorers toward the best places to search for the traces of alien biology. Imagine a future mission, perhaps decades from now, where a lander drills into a Martian ice sheet, melts a sample, and detects something extraordinary. Preserved amino acids, maybe even fragments of DNA or other organic molecules that once belonged to Martian microbes. That would be one of the most profound discoveries in human history, proof that we are not alone in the universe, that life once flickered on another world just next door. But even if we don't find direct evidence of life, studies like this remind us that Mars is still a place full of possibilities. Its frozen landscapes may hold the answers to ancient mysteries, and its ice, more than its rocks or dust, might be the key to unlocking them. In the end, the story of Mars is also the story of endurance, of how the simplest molecules, trapped in frozen silence, can outlast the ages. And as NASA's Christopher House and Alexander Pavlov remind us, those frozen archives could be waiting just below the surface, ready to tell us what once lived, breathed, and perhaps thrived on the red planet. Understanding these frozen processes doesn't just help us search for life on Mars. It also helps us understand how life, in any corner of the cosmos, might survive the passage of deep time. As we continue to explore, one ice core at a time, we're not just studying another planet. We are tracing the story of life itself, preserved in the crystal cold across millions of years. And that's it. Thanks for watching, and if you enjoyed diving deep into the science of Mars and the mysteries of life beyond Earth, don't forget to like, subscribe, and share this video with fellow space enthusiasts. Stay curious, keep looking up, and remember, every frozen world might be hiding a story waiting to be thought. This is Spaceverse, where we explore the wonders of the universe, one discovery at a time.